Every number system serves a distinct purpose. Naturals aid in counting, integers are useful for handling debts, and rationals facilitate working with fractions. Extending this idea, real numbers step in to tackle the challenge of measuring distances accurately. Initially, it might not be evident why we can't solely rely on rational numbers for this task. Imagine navigating through a city using only approximate distances. What could go wrong? In today's episode, we explore the intricacies of rational numbers, shedding light on why they fall short in measuring distances and performing calculus. For a considerable time, the belief held that rational numbers would be sufficient for measuring distances. After all, rationals seem tightly packed. Between any two, a new rational emerges, and you can pinpoint arbitrarily small positive rationals. However, considering the challenges of calculating exact distances, could there be hidden measures that cannot be represented through rational numbers? To answer this question, let's delve into a fascinating insight that has captivated minds since its inception in ancient times. Picture a right triangle with sides each measuring 1 unit. According to the Pythagorean theorem, the hypotenuse would have a length equal to the square root of 2 units. Surprisingly, square root of 2 is not a rational number. If you've delved into mathematical proofs, this might be one of the initial ones you encountered. However, if you haven't seen a proof of this theorem, consider yourself fortunate for the opportunity to ponder its intricacies. Having encountered it a long time ago, I can't help but wonder if I could have deduced it myself. The standard proof is remarkably elegant, making it less apparent how one might conceive it. For now, we'll refrain from revealing the classic proof to preserve the process of discovery for those who haven't encountered it. For those who are familiar with it, now is an opportune moment to contemplate how you would formulate that proof on your own. If you are eager to explore a possible approach or witness a proof, share your interest in the comments section, and we'll consider creating a dedicated video. In the meantime, let's assume, for the sake of our discussion, that there are no natural numbers a and b such that the square root of 2 is equal to a over b. As we deepen our understanding of real numbers, we'll come to realize that, despite their apparent density, the rationals have inherent gaps. Our focus on square root 2 serves as a straightforward example to illustrate this concept. The notion that rational numbers have inherent gaps might pique your interest, but you are likely wondering why this matters. After all, you can get arbitrarily close to any of these gaps using rational numbers, so why not use them to represent distances? While we may not offer a comprehensive answer to this question today, we'll share some insights. Before we present our perspective, we invite you to pause the video, reflect on this concept, and share your thoughts in the comments section. Your insights contribute to the broader discussion and enhance the learning experience for everyone. One might argue that we can approximate any distance arbitrarily well using rationals, and since all calculations in computers are rounded to rational numbers, the presence of these gaps appear inconsequential. However, we contend that filling these gaps is crucial for advancing the theory. The significance of doing so becomes increasingly apparent as you progress in your exploration of real analysis. For now, let's concentrate on a straightforward example to illustrate this point. Consider a function that equals 0 for every rational number whose square is smaller than 2 and equals 1 otherwise. Plotting this function reveals a jump at the point where the square root of 2 would be. Although we haven't defined continuity yet, the intuitive observation of this jump suggests that the function should not be continuous. Interestingly, if we limit our view to rational numbers alone, we have no way of detecting this jump because it occurs at a whole. In fact, once a proper definition of continuity is established, you'll find that this function is surprisingly continuous in the realm of rational numbers. Continuity is a valuable concept, and the fact that the continuity in the rationals contradicts our intuition hints that the rationals may not be the ideal number system for calculus. We'll delve deeper into the intricacies of continuity in a future video. In the meantime, you might ponder the questions: what is continuity, and why is it such a crucial concept in the development of calculus? The limitation of the rational numbers lies in their inherent holes, hindering the formulation of a comprehensive calculus theory. To overcome this, a new number system is needed, one that extends beyond the rationals yet is hole-free. But how can we construct the real numbers from the rationals? Directly addressing this intricate question can be daunting. Thus, let's first delve into the exploration of identifying holes within the rational numbers. Consider this: how can we distinguish the presence of a gap where the square root of 2 should fit? One might naturally assert that we identify a hole when encountering a real number, such as the square root of 2, which falls outside the realm of rational numbers. However, this assertion presupposes that we already possess a constructed set of real numbers. This prompts a deeper inquiry: how can we pinpoint the holes within the rational numbers by exclusively examining rational numbers? Today we introduce three distinct solutions: completeness, the nested interval property, and the supremum property. The initial approach involves utilizing sequences. By a sequence, we mean an enumerated list of elements within a given space. To identify a hole, such as where the square root of 2 should be, we create a sequence where each successive member progressively approaches the potential gap. Consider the sequence 1, 1.4, 1.41, 1.414, and so on, adding one new decimal with each iteration. Once these points are arranged in a sequence, two questions emerge. First, should we expect the sequence to converge, indicating that the elements are rapidly closing in on the whole? Second, does the sequence indeed converge? In this particular example, we anticipate convergence as the numbers steadily approach each other. However, the sequence itself won't converge because the potential limit, square root of 2, is not a rational number. While this intuitive explanation may not meet the rigor of a math course, possessing the correct intuition significantly aids in grasping the more rigorous aspects. Remember, intuition doesn't prove truths but guides us in the search for them. Before we proceed, consider the following questions. Is the intuition of searching for holes in a space through sequences that should converge but do not sufficient? Do you possess any other intuition that could enhance the understanding of this concept? How can we refine and formalize this intuition? Take a moment to pause the video, contemplate these questions, and share your insights with us. Our series aims to highlight aspects often overlooked in mathematical books, such as these intuitions, making your input invaluable for improving our explanations. To rigorously refine our intuition, we need to precisely define what we mean when we say a sequence wants to converge, and when we assert that a sequence converges. Both concepts require us to operate within metric spaces, which are spaces equipped with a function that measures distances. In the case of rational numbers, we'll utilize the absolute value. Once a distance is established, we can declare that a sequence converges to a point x when, no matter how much we zoom into that point, all but a finite number of points in the sequence fall within the region we've zoomed in on. This leads us to the classic definition of convergence. A sequence xn converges to x if for every epsilon greater than 0, representing the size of our zoom, all but a finite number of xn are at a distance smaller than epsilon from x. The all but finite part can be expressed as stating that there exists a capital N such that for every n larger than capital N, xn lies at a distance smaller than epsilon from x. When you encounter this definition for the first time, it may seem a bit convoluted. However, if you recall the intuition, you should be able to reproduce the definition on your own. Does our intuitive explanation enhance our understanding, or does it create confusion? Feel free to let us know. If the definition appears perplexing initially, give it some time. In any case, we'll revisit the definition later. Currently, our primary focus is on developing a solid intuition. The primary challenge with the convergence definition is the prerequisite knowledge of the convergence point. This limitation renders the definition insufficient for determining if a sequence wants to converge. To address this, we require a means of expressing that the points in the sequence are gradually getting closer without referencing any point outside of the sequence. After thorough consideration, Cauchy devised a rigorous way to describe this, now known as the Cauchy criteria. A sequence is Cauchy, or colloquially, it wants to converge if, for every epsilon, once again representing the zoom-in size, there are only finitely many points not closer than epsilon. It would be beneficial to contemplate how would you articulate this mathematically, so feel free to pause the video and reflect. For those who've already tackled this or are here for the journey, let's state that a sequence xn is Cauchy if for every epsilon greater than 0 there exists a capital N such that for every m and n larger than capital N, the distance between xn and xm is smaller than epsilon. Once again, if the formal definition seems perplexing, keep it in the back of your mind. We'll delve into it in more detail in the future. Armed with a formal definition of convergence and wanting to converge, we are now equipped to systematically identify holes in our metric space. We categorize a metric space as having holes if it harbors Cauchy sequences that do not converge. Otherwise, we will say that the space is complete. Consequently, one approach to constructing the real numbers involves creating a space that encompasses the rational numbers while ensuring that every Cauchy sequence within it converges. How could you devise such a completion? Although we won't delve into the answer in this video, take some time to contemplate the question. When you feel prepared, dive into our next video where we explore Cauchy sequences and completions in greater detail. The second method for identifying holes involved confining the hole within a series of closed intervals that progressively diminish in size. To illustrate this with the case of trapping the square root of 2, we can consider intervals such as 1, 2, 1.4, 1.5, 1.41, 1.42, 1.414, 1.415, and so on, with each new interval's length being 1/10 smaller than its predecessor. In a space devoid of holes, the intersection of all these intervals should converge to the point we aim to enclose. However, within a space containing holes, the intersection may be empty. Once again, I encourage you to pause the video, reflect on this intuition, and contemplate ways to formalize it. These contemplative moments are what makes mathematics an engaging pursuit. If you are ready to proceed, it's crucial to note that formalizing this intuition requires the ability to define closed intervals within our space. This, in turn, necessitates an order relationship, such as smaller than or equal to. In spaces equipped with an order relationship, like the rationals, we can define a closed interval AB as the set of numbers greater than or equal to A and less than or equal to b. Similarly, open intervals can be defined using strict inequalities. As you delve into the intuition behind our approach, consider why we opt for closed intervals instead of open intervals. Feel free to share your insights with us. Now, driven by our intuition, let's establish a formal definition. We define a sequence of intervals an, bn as nested if each interval is contained within the previous one. Specifically, for every n, an plus 1, bn plus 1 contains an, bn. A space is said to possess the nested interval property if every collection of non-empty closed intervals has a non-empty intersection. The rational numbers do not have the nested interval property, as we can, for example, devise a sequence of nested intervals that enclose the square root of 2. Conversely, our aim is to construct the real numbers in a manner that ensures they satisfy this property. The final method for identifying a whole once again draws on the order structure of the space. The fundamental concept involves considering a set A of all elements strictly smaller than the point we want to examine, along with the set of upper bounds of A. To illustrate, let's examine what happens when we test the number 1. In this case, the set A is the collection of all numbers strictly smaller than 1, while the upper bounds are all the numbers greater than or equal to 1. Notably, this set of upper bounds has 1 as its least element. However, when we perform the same test for the square root of 2, the set of upper bounds lacks a least element. This observation suggests that the presence of a least upper bound can serve as a criterion for evaluating the existence of wholes. Now, as is customary, take a moment to pause the video and delve into the intuition behind this method. Your reflections will undoubtedly enhance your grasp of the subject, so, as always, your comments are highly valued. Ready to continue? To formalize this method, we once again rely on the order structure of the space. We say that U is an upper bound of the set A if U is larger than or equal to every element A in A. A set A is said to be upper bounded if it has an upper bound. The least upper bound of a set is the minimum of all the upper bounds of that set. Note that the minimum and maximum of a set are expected to be elements of the set. For example, the closed interval 0, 1 has a minimum, namely 0. However, the open interval 0, 1 does not have a minimum since 0 is not part of the set. Once you play around with least upper bounds, you realize that they are similar to the maximum of a set, but with the advantage that they don't need to belong to the set under consideration. For example, the open interval 0, 1 does not have a maximum, but it has a least upper bound, namely 1. Least upper bounds turn out to be so important that they have a special name. They are called the supremum of a set, often shortened to sup. With these definitions in place, we are ready to establish the supremum property. An ordered set is said to have the supremum property if every non-empty and upper bounded set has a supremum. The rational numbers lack the supremum property because they have wholes. For instance, the set of rational numbers smaller than the square root of 2 does not have a supremum in the rationals. Can you discern why? Take your time to ponder this and feel free to share your answers or seek assistance with this challenge in the comments section or on Discord. In summary, the rational numbers harbor inherent gaps that render them unsuitable for calculus. We examined 3 properties: completeness, the nested interval property, and the supremum property, that aid in identifying the presence of gaps in a space. The completeness property relies on the distance function, while the nested interval property and supremum property are grounded in the order relationship of the space. Our next objective is to expand the rational numbers into a new set incorporating at least one of these properties. The pursuit of completeness leads to a distinct construction separate from that arising from the nested interval property or the supremum property. Despite these differences, the common thread of addressing the existence of gaps ensures that any extensions of the rationals adhering to one property will also satisfy the other two. In essence, constructions aligned with these properties are, to some extent, equivalent, collectively yielding the real numbers, a topic to be explored in upcoming videos. Alternatively, we can axiomatically treat the real numbers as an extension of the rational numbers, satisfying the supremum property. This axiomatic approach establishes a robust foundation for delving into calculus, and indeed, we will adopt this perspective in our explorations. While you await the exploration of these topics in subsequent videos, let's contemplate some questions. Are there other scenarios where the existence of holes in the rational numbers proves inadequate for calculus? How can we demonstrate the derivation of the nested interval property from the supremum property? Conversely, how can we establish completeness from the nested interval property and the supremum property from completeness? Is there a way to provide an axiomatic description for the rational numbers? What about an axiomatic description for the reals? We welcome your insights on these topics or any other question that cross your mind. Until next time, happy pondering.